Hello everyone, welcome back to another video. Today we are going to be coming up with a model to represent the heat diffusion or the heat profile of a bar right here. So we are going to have this bar that's going to be a certain length, and pretty much what's going to be happening is that the heat is going to be diffusing throughout the bar, and we are going to be coming up with a model that is going to show how the heat changes throughout the position of the bar at different times, all right? So we are going to have our graph, and then we are going to have our position at the bottom and our temperature on the left right here. And pretty much, let's pick a certain time. Let's say we want to come up with the heat profile at t equals 5 seconds. And it's going to look something like this at t equals 5. All right, this is going to be the graph at a certain time, but we're going to be taking the heat profile at many different times, and eventually this is going to become a linear relationship after a certain amount of time. It's going to balance out into this linear relationship right here, and we're going to be coming up with a model to represent this, all right? So the first step that we are going to be doing is we are going to be bringing in the heat diffusion equation that we derived in our last video. So if you want to see how we came up with that, be sure to check out our last video. And we know that there's going to be no heat generation or heat being lost in this bar. So we're going to leave out the heat generation part of that equation. So we're not going to have to use that. And we are also going to know that this bar is going to be starting out at room temperature, right? So those are just a few quick parameters before we get into this. So now we're going to go ahead and bring in our heat diffusion equation. So we had the second derivative of the temperature as it relates to the position. And then we had our heat diffusion variable right here. And then we also had the derivative of the temperature with respect to time. All right, and now what we're going to go ahead and do is we're just going to multiply both sides by our heat diffusion variable over here, just so we don't have this 1 over right here. Make things a little bit simpler for us, so that's going to cancel out over here, and just leave this over here like that. All right. Now the next thing we are going to want to do is we are going to approximate these derivatives right here, okay? And we're going to do this by pretty much just looking at a small change in time and a small change in position. This should be a little t over here to symbolize our time, using big T to represent our temperature. So in order to approximate these, we are going to be looking at a small specific change in time and a small specific change in our position along the bar. And we can go ahead and write that out as delta x to represent a small change in our position. And then we can also use delta t to represent a small change in time. And then after that, we can go ahead and bring in some accounting numbers. So that's pretty much just going to be 0, 1, 2, 3 integers. And for our position, we can use j for that. So j is going to be equal to 0, 1, 2, 3, basic integers right there. And then for our time right here, we will go ahead and use n. So n is also going to be equal to 0, 1, 2, 3, so on and so forth. All right, so we know that our position over here is just going to be equal to our j times our change in position, right? And then we know that our time is going to be equal to n times our change in time. So we'll go ahead and write that out. So x is going to be equal to n because we're using this as our counting number. We are actually using a j to represent our counting number for position. So this is going to be equal to j delta x, and then our temperature or time, excuse me, is going to be n delta t, like so. All right. And again, we are using an explicit method to try and come up with a simplification for our derivatives right here. All right, and now we'll go ahead and get into that. So I'll go ahead and erase all this right here. All right, so for our first one, we are going to be coming up with a simplification for our change in temperature as it relates to the change in position. And again, we had a second derivative for that. It was the second derivative of temperature with respect to position. So this one's going to be a little bit more complicated than we do it with when we do the derivative with respect to time, because with respect to position, it was the second derivative. So we're going to have to, this one's going to be a little bit more complicated. So we'll go ahead and get that knocked out of the way first. All right, so we'll start out with our delta t, delta x. All right, so in order to come up with this, let's go ahead and think about this a little bit. So we are cutting up our position into lots of little fragments using what we just did, our counting numbers over here. So that we're going to be looking at a lot of different segments, all right? And the distance between each of these is going to be our delta x, right? And in order to approximate our temperature, we are going to be wanting to look at the difference between the temperature at, say, this position here, this J position, and then we are going to subtract that from the temperature that we had at the previous position, our J minus 1 right here, and then we're going to divide that by the difference in the position, our delta x, all right? So this is all going to be over delta x, right? And then we are going to have our initial position right here. This is going to be our j plus 1, and then that is going to be subtracted by our tj right here. All right, so we'll go ahead and write that out. So this is going to be our tj plus 1 of n, and then that is going to be subtracted by our t of j of n. And this is going to be our approximation for the first derivative. But now we have to go ahead and look at how this as a whole is changing with respect to the position. So we are going to have to take the second derivative of this, all right? So we'll go ahead and write that out now. All right. So what we are going to want to do now is we are going to have to subtract our starting position, our Jn, from the one previous to this. That is going to be J minus 1, all right? So we'll go ahead and do that. This as a whole is going to be, this term is going to be subtracted from that term. So we're going to have to include a minus over here. So this is going to be Tjn minus Tj minus 1n. That is again going to be over delta x. All right, and then this as a whole is going to be divided by delta x again. There we go. And as we can see here, we have two j minus n's, and this is also going to be subtracted. So this can become 2 minus 2 jn, and then we have a minus over here, and this is also a minus, so those will cancel and become an addition. And then we have all of this over delta x, and then another delta x on the minus, so this is going to become delta x squared. So we'll go ahead and simplify this term down quite a bit. So we know that the second derivative of the temperature with respect to position, we will say that is going to be Tj plus 1 of n, and then we had minus 2j of n, Jn, and then these subtractions are going to cancel out, making this a plus. Try to write this a little bit bigger to make sure you guys can see this. and then this is all going to be over delta x squared. All right, so this is going to be our approximation for the second derivative of temperature with respect to position. Now we'll go ahead and work on our simplified expression for the temperature with respect to time. All right, so now we are going to come up with our approximation for the change in temperature as it relates to a change in time. All right, and in order to do this, we are going to be looking at what that temperature is going to be at a certain position at a future time, and then we're subtracting that from the temperature at that same position from a previous time, and then dividing all that by the change in temperature, all right? So that is going to look something like this. It is going to be at position J at an n plus 1 of future time right here. And that is going to be subtracted by t j of n. This is going to be the previous time. And then that is all going to be divided by a change in time right here. All right, so this is going to be our expression for the partial derivative of temperature with respect to time, all right? And now we're going to go back to our equation that we wrote up at the start of the video and substitute these on in. So we'll go ahead and do that now. Go ahead and erase this right here. All right, so we've gone ahead and substituted our expressions into our heat diffusion equation over here. And now we can go ahead and do some simplifying. But first, before we do that, let's go ahead and talk about what we're going to try and isolate in our equation. In other words, what we want to have on one side of our equation and have everything else on the other side of the equation. And the term we're going to want to isolate right here is this t j plus 1 over n, right? Because this is going to tell us the temperature at a next time step, right? So we are going to want to come up with a graph that is going to give us how the heat is going to diffuse at certain times. And basically what this term is going to be giving us, it's going to give us the temperature at that next time step. So this is why we want to isolate this right here. And in order to do that, we're going to multiply this change in time over and then add this tjn over. And when we do that, we can also take out this delta x squared outside the parentheses and put it outside. And when we do that, we are going to get this, we're going to get delta t multiplied by our variable over here over delta x squared. And that as a whole is going to be a new variable r that we're going to use later on in our Python. So r is going to equal, and then this is going to be delta t over delta x squared right here, as you can see. So we can go ahead and bring this out, multiply that over, and then we're going to have r that's going to be factored out to all of this. And then over here, we already have a tjn right here in both of these. So that's going to be factored out. That's going to become 1 minus 2r of tjn. It looks like I actually forgot to write my t in here, so I'll go ahead and write that in there now. Alright, so now we can go ahead and simplify this out. So once again, we are going to have this isolated out front because we want to give that future time graph. Alright, and then this is going to be r t j plus 1 n, and then once again we're going to have 1 minus 2r. This is going to be subtracted, 1 minus 2r tjn, and then we are going to add r tj minus 1n, and there you have it. This is going to be our expression right here for the temperature step, for the time step of this bar right here. And now we'll go ahead and hop into Python so we can go ahead and code this out and work on creating our graphs. One more quick note before we hop into Python. This does need to be added instead of subtracted right here. We already accounted for this minus in our factor right here because this is 1 minus 2r, because this is going to be added over. So this 1 is going to be positive and the 2r is going to be negative, so we already accounted for that. And yeah, we'll go ahead and hop into the Python now. Alright, so there's one more quick typo that we needed to fix before we hop into Python. We had this as j plus 1, which is going to give you the temperature at the future step. That is not what we wanted to say. We wanted to say this is of j of n plus 1 because we wanted to get the temperature at the future time step, not the future position step. So this is going to be j n plus 1 right here. Very important right there. Want to make sure we get that corrected before we hop into Python, and we'll do that for real this time now. Alright, so we are over here in Python now, and we are going to go ahead and start working on our plot to show how the temperature is going to diffuse along our bar as time goes on. And we are going to be using NumPy and make subplots over here from Plotly to do this. And over here I've gone ahead and already added all of our constants that we're going to be using. So we're going to have our thermal diffusivity, our alpha over here is going to be 1 meter squared per second. Then we're going to have over here our position step and our time step, which is 1 meter and half a second. And then over here we have our R expression that relates all these constants up above to each other. And then down here we are going to have the initial temperature of our bar, which we said was going to be room temperature, which is about 20 degrees Celsius. And then, of course, we are going to set the temperature of the left side at 50 degrees Celsius and the right side to 80 degrees Celsius. And then down here, this n is going to be the length of our bar, which we are going to say is 20 meters. So we are going to have 20 position steps, right? Because we have a 20 meter long bar, and our position step is 1 meter, so 20 divided by 1 is going to be 20 different steps. So we are going to first create our position, which is going to be our x-axis, right? We are going to be graphing the x-axis, the position along the bar on the x-axis, and the temperature at each of those positions. The temperature is going to be the y-axis. So in order to set up our x-axis, we will give it the variable x, and this is we're going to use the arange function, and we are going to set this as n for the variable for it. I think this might just be 1a. Alright, there we go. Alright, so we got this running now, and basically what this arange function is going to be doing is it is going to give us the evenly spaced position intervals along our 20 meter bar, and we're going to be taking the temperature at those evenly spaced intervals. And so we'll go ahead and set up our temperature now. So for the temperature, which is going to be our y-axis, we're going to be using the full function. And we want this to be based on our n over here. We want this to have the same number of intervals, so we're going to go n. And then we want this to start out as our room temperature. We want the initial temperature along the whole bar to be our room temperature, so we'll now go TO, which is going to set it at 20 degrees Celsius. Here we go. All right, and now obviously at the initial point, when we first add our heating to the left and right side to make the initial temperature be 50 degrees Celsius on the left side and 80 degrees Celsius on the right side, we're not going to want that to be room temperature anymore, all right? So we are going to have to use just some basic calling over here. This T0 is going to give us that initial value in the array, the leftmost value, which is going to be our left side, this T0, and we are going to want to input that as 50, or I guess we should just use TL here in case we want to change this up later. Say we want to make it 60 degrees on the left side, we can just input 60 over here instead of having to come down to our function and do it. And then to get to our rightmost value within the array, we'll just go -1. That is going to give us the rightmost, or the last value within the array, and we will make this our TR over here, the heating on the right side. So this is going to give us our initial setup, the temperature along the bar to start. But now we're going to have to include a for loop in order to model how that heat is going to diffuse and how that temperature is going to rise along those intervals within the bar. So we're going to need to bring in a for loop to do that. Alright, so now we're going to go ahead and create our for loop, which is going to give us the temperature at all those in-between position steps. So we're not going to want this to update the temperature at the leftmost point and the rightmost point, because those are always going to be 50 degrees Celsius and then 80 degrees Celsius at the endpoints. So we're not going to need those to update. So we're going to need to create a for loop that's only going to update the temperature at those in-between points. And we are going to use that equation that we came up with in the earlier part of the video on the whiteboard to do that. But first we need to go ahead and create our for loop. So we'll say for I in range, and then we'll just go from 1 to 100 for now. Not sure if this will be enough, but this is going to give us 100 separate graphs, and it's going to run through and create that temperature at each position 100 different times. It's going to run through our time step 100 different times, and we'll see if this is going to be enough. And we'll know if it's enough or not based on whether or not we get that linear relationship to show that the heat is done diffusing. So we'll see if this is enough to get that. And in order for this to only give us the in-between points, we are going to need this to update from 1 to -1. This is going to allow us to skip updating the first and last value in our array. And the right side of this equation is just going to be that equation that we came up with earlier on the whiteboard. Pretty much this represents the temperature at the future time, that n+1 that we came up with, and then the rest of this is simply going to be the equation that we came up with for earlier. All right. So we had R times T, and then this was of the future step. So this is going to, at the future position, that next position along that line. So in order to model that, it is going to be 2 colon right here. That is going to give us the temperature at the next step. And then we also had the temperature at the previous step, which is just going to be colon -2. Pretty much the same thing as this. So this is going to be R times T of colon -2. And then in between this, we also had the temperature at the current step, which we had a factor of 1 minus 2R. So this is going to be 1 minus 2 times R right here. And then this is all going to be getting multiplied by our 1 to -1 because it is looking at the current position step. So this is going to be times T of 1 through -1, like so. And this is going to be our function right here. This is going to give us the temperature at all of the in-between intervals. Now the way we have it set up, this is going to give us 100 separate graphs, which is going to be a lot to look through. So what we're going to do is we are going to use a divisor. So we are going to divide this, whatever our I value is, by 10, and when that remainder is going to be 0, we're going to say that's when we want to graph it, all right? So that would give us 10 graphs instead of 100, right? Because say we're on the 7th step and I is equal to 7, we're going to divide that by 10. And of course, the remainder of that is not going to be 0. So that's not going to graph that. It's only going to graph it when I is 10, 20, 30, and so on. So we are going to go I, and then in order to do that, we use the percentage sign. So I 10, and that is going to be equal to 0. That is when we're going to want to plot that. I think we need to use if function here, if I is that, and then we're going to go ahead and need to create our plot, of course. So we'll go ahead and create our plot now. Alright, so we are going to go ahead and create our graph now. So we are going to name it Fig. Fig equals make subplots. This is going to create our graph right here. And then we'll need to make that our initial graph when it is 20 at 20 degrees Celsius at all the in-between points, and then 50 on the left and 80 on the right. So we're going to go fig.add scatter. And then our x is going to be equal to x because this is going to be our position values over here. And then our y is going to be equal to our temperature values. And then our mode is going to be lines. This is not going to be a scatter plot. We're going to want to see the lines for this. All right, and then we're going to name this, and we'll use f for that. And this is just going to be 0 because this is going to be when time equals 0. This is going to be the initial plot right here. All right, and then we need to go ahead and down here, we'll just go ahead and copy and paste this in because it's going to be pretty much the same thing. The only thing we're going to need to change is our name over here. We are going to include some brackets so that we can actually change this. And then this is going to be equal to our time step multiplied by whatever I we are, right? So say we're running through this for loop for the 10th time, so I is equal to 10. We're just going to say that's 10 multiplied by our time step. So every time I is being run through in our for loop, a half a second is passing. So a half second passes 10 times. We're going to need this to say that this is 5 seconds long. So we'll have that like so. And that's pretty much going to be it for our for loop. We'll see how this is running. Doesn't look like we have the proper syntax here. Alright, so I did figure out what the syntax issue was. We did forget to include this extra parentheses over here to close this out, so that should be running fine. So now we'll just go ahead and copy down this add scatter down here because we're going to be using the same x and y axes for this. The only thing that's really going to be changing is what we name this. So what this is going to do is every 10th iteration through the for loop, it's going to be creating a new graph, so pretty much every 5 seconds. And instead of naming this 0, we're going to include some brackets, and we're going to say that this is going to be equal to I times our time step. And so say, like, in order to explain this, so I pretty much is every half second, right? So every half second we are running through and we are creating a graph to model the temperature at every half second. But since we are including the graph every 10 times, this is going to be pretty much every 5 seconds, right? Because our time step is a half second up here. So when we include the graph, the first one is going to be at 10, then 20, then 30, right? Because that's when you divide it by 10, the remainder is going to be 0. So this is just going to be multiplying whatever iteration we are through the for loop is going to be multiplied by the time step. So that is going to be giving us the name of the graph. Alright, and we'll see what this is looking like here. We'll go ahead and run through everything else as well. Make sure everything is good. Expecting, did not include our end bracket over here. Alright, and then we'll need to update the layout. So fig.update layout. And we'll just go ahead and change the width and the height. We'll make those 700. That is not how you spell width right there. We'll make the width and height 700. You could also do things like change the color of the graph. We're not going to mess with all of that right now. We'll just include the width and height for now. And see what our graph is looking like here. And it's looking pretty good. As you can see, we are approaching linear. It's becoming more linear. But we have not included quite enough time yet. So pretty much what we're going to need to do is we're going to need to increase the range of our for loop over here so that it is running for a longer time. We'll just include some like 400 here. see if we get that linear relationship, and there you have it. So this is it. This is the model of how the temperature at those interior steps is going to be changing once you begin heating the left and right ends of it. As you can see here, it starts out with the points nearest to the ends getting heated up first, and then that heat begins to spread its way towards the middle before eventually in the end it creates this linear relationship with the heat increasing from the left point to the right point, obviously because the right point is being heated to a hotter temperature than the left point. And yeah, that is going to do it for today's video. In the next video, we are going to be looking at how this time step is going to be affecting this relationship over here, because once you increase this time step by more than half a second, things in this graph begin to get a little wonky. So let's say we wanted to make this 0.51 instead of the 0.5 that we had before. Let's take a look at how that is going to impact the graph. And yeah, as you can see here, this is not at all what this is going to look like in real life. So we're going to be taking a look at why that is in the next video. So I hope you guys will check that one out. And yeah, make sure to have a good day. Like the video if you enjoyed. Comment down below what you want to see next, and take care.